So we're back again, and as a reminder, down below the video, there should be links to, it'll have the chapters of this video indexed, and then we combine that into a big index. You can click on the link and get like 3 years of indexes for all the stuff we've done. That's also got the ROS agriculture indexes, which that goes back like 6 years or something until that. So there's 3 years of that. We got like 3 years of the new stuff, and there's a couple other links there. I forgot what they are. So you can dig through those. Okay, that's all I'm going to say about that. It's sometimes I need to write up a script for that, or go ahead and I keep wanting to move all that crap into another place and just point to it and say, here, go watch this video of me babbling, and then down below that will be all the links, so they'll just be in one spot, and it should work out better that way. So we were talking about several things. Last couple of weeks we were talking about motor drivers. Bob bought a new one called HDT. Here, let me look. Well, here it is right here. Bigger. I've got it up on my screen, which is not sharing, but it's a DBH-12 board, and it's on Amazon. Let's see, how long would it take to pull this up on Amazon? Let's go here. Okay, go there. Amazon. So I search for, what did I say? HDB-12V. And it's interesting. I don't know why people do this, but let's see, screen share. Well, that didn't work. So of course I wasn't on Amazon when I did the search. This is why I was saying we should talk about this stuff before we start recording. So now here I've got a mess that I've created. So I copy this, go back here and say Amazon. I'm going to share my screen here, share screen. And that would be desktop 2. Okay, so I'm assuming you can see my screen. It's going to show me. Okay, there looks like it showed up. So if I go back here, I go to Amazon. All the stuff's in my way. One more time. Go here. If I start screaming, just ignore me. Amazon. Okay. Go to Amazon. Put in this. And the whole point, I just wanted to make the. I think it's here's the 3 different boards that were talked about. I probably in this video. I don't know if I showed it yet or not. Anyway, search up this board, and there's several different ones. I just grab a cheap one here. And if you look at it on the side of the board here, it says model H. There's a DBH-12V. But if you look at the Amazon stuff, it says DC5 12 volt, blah, 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 blah. No, I don't think anywhere in here they mention the actual model number that this board would be known by. So, but if you search for this DBH-12V, it will pull up this page and show you that stuff. And I just found it interesting that, it's got a perfectly good part number on that somebody made up, but they're not going to show you that. Well, if you search for it, it finds it. So anyway, this is that board that Bob had bought. It's a dual channel. They claim to run 30 amps, and it's got this interface down here of it's got an in1 and an in2, so that's like forward enable and reverse enable. And it has an enable pin to turn that channel off completely. And the CT, I think, is current output, so it measures the current and presents that as a voltage. And then it's got a ground. Now, if here, let's move on to that guy's video next, if it's still up here. There was a guy talking about driving this board. And again, I could try to see if I can get the sound to come up, but everybody said it didn't work. So anyway, if we go to this guy's video here, this link will be in the video. If you go out to his at 38 minutes and 54 seconds, he says it's the DBH-12 dual H bridge. So if I go to that location in the thing here.
So we've already looked at 4 different motor drivers, and we can see that for small motors.
So is that sound coming? Can you hear the guy talking?
I can a little bit.
Like he's in the other room talking. Yes, you can hear him.
Yeah, okay, well, we'll go with that then. So anyway, he's talking about this board, and it gets up to the first thing. He shows a picture of the board. He says these are the pins are, and he gives you a warning there. And I'll let it play through that and see if that works.
Input, not an output. There are many
Said, oh, that was it right there. He said, "Oh, come on."
So we've already looked at 4 different motor drivers, and we can see that for small motors, between the 4 of them, there's probably a perfect selection for your project. But what if we have a very large motor, one that consumes a lot of current? Obviously, the drivers we've looked at so far won't do the trick, but there are larger drivers that we can use that can handle a great deal of current. So let's take a look at a couple of them right now. The DB812 is a dual DC motor driver with impressive current capabilities, and it's part of the DB81 series of drivers. This driver will support a motor voltage from 5 to 14.5 volts. It can handle a continuous current of 20 amperes and a peak current of 30 amperes. The DB812 supplies its own logic power supply and uses a logic voltage of 3.3 to 12 volts. Here's the pinout of the DB812 module. Note from the truth table that this motor is controlled in the same method that DRV8871 is, by applying a PWM input to one pin and a low input to the other pin, which can control both the speed and direction. There is an IN1 and IN2 pin for both channels A and B. The EN line is the enable line, and this is internally held high. You can pull this down to ground to disable the bridge.
So I see I should have tracked this down a little harder before I started playing this. We didn't really need to do all this. He's about to get the point where he says, "Oh, by the way," he says, "this pin right here is not a 5-volt input," and that's what he's about to explain. So he'll say that. He says, "Don't hook it up; it'll blow up your Arduino." And then the next page he'll say, "Here's his recommended thing where he's got it. He's got his ground and his two control lines for each motor channel hooked up, and he does not hook the 5 volts up." So I'll let this play through here.
CT is the current monitor, and this can be set out to an analog input if you wish to monitor the current consumption of the H-bridge. One important note with this H-bridge is that you should never drive it at 100% speed. You should not go over 98% speed with your pulse width modulation signal. Another important note is that the V+ pin on the connector is connected to the same motor V+ on the terminal strip, and this is an input, not an output. There are many diagrams on the internet that show this as being an input and show it being connected to the logic voltage on your microcontroller. This is not true, and doing this will destroy your microcontroller.
So that's a handy thing to know right there. If you do it, it will blow up, and everybody on the internet showing it connected. So hey, now he's going to show a diagram of it connected the way he wants it.
The way that you hook a DB812 up to an Arduino Uno. As you can see, there's no power sent from the microcontroller, only a ground connection. Otherwise, we're just using the 4 input pins, IN1 and IN2 for channels A and B. You can change the pin assignments if you wish, but remember, all of these pins need to be able to support pulse width modulation.
Tony, I thought that was pretty important to point that out because, yeah, you don't know. And he went to trouble to figure that out. He probably blew up a couple of boards before he figured that out. And if you back up the beginning of this guy's video, DC motor basics, let's start here.
For a motor driver. The motor drivers we're working with today are for use with a DC motor, which is probably the simplest type.
Well, I wanted the thing where it shows.
Today in the workshop, we're working.
See, he's got these 3 big ones across the bottom. He's got a bunch of small ones at the top. And he goes through each one of these boards and tells you the pros and cons of each one. And so this is a good video to go through and watch this whole thing, and then pull up, 2 or 3 other videos doing the same thing. And then if you have a specific board, search up those. Like for instance, down here on the screen, here's got 2 of those IBT2 motor drivers. That's the one in the center here, and the one like I and Al are playing with right now. And he's saying, here, hook this up to an Arduino on a pot, and he can run his 2. He's actually got a joystick on it down here. So he's got a joystick hooked to something like an Arduino, 2 driver boards and 2 big motors. So you can go through like that and look up the for a specific type of motor, do a search on that and get lots of different people giving you opinions on that. And so back to this problem about if you hook up the power to that one wrong, I think even on Amazon when you go to buy it, I thought it gave you a diagram here. Maybe it's just depending who's selling it, they give you the diagram or not. And some of them show you, yeah, they say hook that right up to your 5 volts on your Arduino, and the guy says that will blow up your board if you do that, because if you got, say, a 12-volt supply driving your motors, that's going to put 12 volts back into your Arduino, power supply, and that's gonna blow out everything if you do that. So now I forgot where I was, other than, I just wanted to point out, if you watch that video, he shows several different boards here. I'll play this here so he moves his hand. Or here, let me back up. So right there across the bottom, here's the 3 big ones, and then here's the these 2 at the top are the L298s, which are I think that's a dual channel motor driver. They're like 2 amps, but they're old and they're bipolar and they generate a lot of heat. And then across the middle, he's got the newer chips from like SparkFront and Adafruit. So basically, these will do the same thing these big boards will. And I don't remember what the cost was, but some of these boards, I think this one here in the middle is a dual channel, and these might be single channel boards. So anyway, this video is worth watching just to get a rundown on all this stuff. So I'll move on from that one. And again, you just search through, so say go to YouTube and search up motor driver Arduino, or just motor driver boards or something like that. It'll bring up a whole list of things, because there's other people that say, here's 4 or 5 boards I played with, and they're showing you how to hook them up and what to do with them. So that is good to know. And just listen to him go through the whole video. How long was this? Like a half an hour or something? Oh, it's an hour. It's an hour-long video. If you listen to the whole thing, he does give you a lot of good points and things to think about. So it's probably worth watching if you got nothing else to do. So let's see. I just want to point out I found that, and that gives information on stuff. And I was playing with my board, my IBT2 board, and last couple of meetings, I was looking at Al's diagram and says, well, you don't have 5 volts hooked up to your motor. And he says, oh, you don't need that because it supplies 5 volts. And I thought, oh, that can't be, because you look at the schematic. Let's see, how can I find that if I say IBT-2? And actually, I should have gone to Amazon instead. Let's go to Amazon and say IBT. IBT-2. Now we pull up a random board here, random manufacturer. And then over here, they give you a schematic. So if I go like this, click to see full view. So if you go look at this, here's your power connector coming in for your motors on this side, and that's connected directly to both driver chips. These are half bridge drivers. So this is 1/2 of your H bridge, and this over here is the other half of your H bridge, and this is out to the motor. So nowhere there does that battery power do anything. And the rest of these things here seem to all be input pins on the driver chips themselves. And then coming over here, they ran everything, all the input signals, they ran it to this logic chip. And so that way it buffers the signal coming in, so you have less chance of blowing things out, and it keeps things more uniform. And then on that header connector, it's got a VCC pin, and then on the chip's got a VCC pin, and that's the only place VCC goes on this board. And otherwise, all these pins down here on this header down there go directly to input pins at this logic chip. So that means if you put a logic high on say A1, that's driving a logic high into the thing. And normally, if it's powered up like it's supposed to be with 5 volts on, then the output follows it and does what it's supposed to. Now, if you don't have the 5 volts hooked up, and you tie these, I don't remember which is which. There's two enable pins. They tell you to hook those up to 5 volts. So if I take 5 volts from my Arduino and hook it up to these two enable pins, it still runs, which momentarily baffled me. But you got to remember that a chip like this has built-in static protection diodes. So if the input tries to go above, if it has a diode to VCC, so if it tries to go above VCC, it conducts to your VCC pin to eliminate, like say, a static discharge or something. But if you don't have any power on VCC and you put power here, well, then the diode conducts and pushes the VCC up to whatever level is coming in on this input pin here. So if I have my two inputs tied to my two enable inputs tied to 5 volts, then that's going to internally in the chip push up the 5 volts, and everything's still going to run and everybody's happy. That's not the way you're supposed to run these things, but that does work. And then as soon as you start doing a PWM, you're going to have two enable pins tied, and then one of your PWM pins, when it's bouncing up and down, it'll also conduct, so it'll give you more power to run that chip. So anyway, the bottom line is, let's see, did they give you a diagram here to hook this up? My thought is you want to hook the two enables and the VCC pin to the, here we go. And I don't like the fact they've got a mixture of JPEG and pastel colors on top of a gray background, because it's just hard to read all this stuff. But they're saying go ahead and hook up. They're saying from the controller board, which is where they would call it a BTS 7960, which is actually, that's the chip that's on the board. That's not the board. That's another annoyance I have, but that's the way it goes. So anyway, they say take the VCC from that board, hook the 5 volts on Arduino, hook the grounds together, hook the two enable pins to 5 volts, and then you got your two PWM inputs are going to PWM pins on your Arduino. If you look over here, that's what they're showing you here. It's confusing because, can we zoom in on this? I don't know if it's worth doing that right now. Anyway, they show using the fritzing type method. They show on the board the 5 volts coming to that pin connector, and it's not obvious, but that the pin in the middle is not connected. The one that says VCC, they put a red dot on it, and then the two enable pins, they put a red dot, and then it just it goes over the top of the other pin that it's not actually hooked up. And that's evidenced by looking at this chart down here. Those are, I think, IS pins or something. And see, those are not connected. They're just floating out there. But they're saying, go ahead and hook power up to the VCC, and then they just drive the two PWM pins, and they say it should just work great. And that's basically what I just did here on mine. And I had it wired up like this. I had some code that was running the motor back and forth. And what I did was I thought, well, what happens if I unplug the VCC pin? So I unplugged that, and it just kept right on running. So it means, yes, it is being powered through the two enable pins, because that's the only place I have that's supplying 5 volts into this thing. Oh, except for the PWM when it's running. But if it's not running, then you don't have anything there. So anyway, that's something I ran across. And I'd say if you use one of these boards, yes, hook that VCC up to a known good 5 volt supply. Which part of that comes back to Bob's issue on his VEX controller. That seems to be a mystery part that I can't find any information on that. And he mentioned that it's a VEX V5 controller. But if I look up a VEX V5 controller, that's not what he has. So I don't know. As I say, I can't find a model number or part number or anything for what he has. So when I go search for it, I can't get anything to turn up. But anyway, the point on that was, I think he said he went out and he measured. I remember how he worded that. I can probably pull it up on Slack here, but he said something about, I think he said he measured it. So it's like a 3-pin, what he's calling a motor connector. And I think it's basically it's like an RC pulse output. So it's got a ground. It's got the PWM pulse coming out, and then it's got a power pin. But it looks like the power pins on that one are putting out 8 to 9 volts, and not the 5 volts that you would expect. So don't plug an RC servo into one of those, because they're expecting 4.8 to 6 volts. And it looks like possibly he hooked up his motor driver, which is a fairly expensive motor driver, and plugged it in. It was expecting to get 5 volts, but the thing was actually putting out 8 to 9 volts, which might just be coming directly from the battery that he's using. I don't know where it's coming from. But anyway, that's something I noticed when I was digging through all this stuff. And just finding various things, because Bob posted a whole bunch of stuff on Slack from like Vex forums and so forth. And I noticed they were talking about 8 or 9 volts, and they're always talking about this MC28 motor motor controller. That's the one that they make, and you plug it into that connector, and it's apparently expected to see that higher voltage to internally they regulate it down for the logic, and then their motors apparently are running at the 8 to 9 volts. So in that case, it's always good to measure voltages before you start plugging stuff in and see, does it match what you expect it to be? And on standard RC servo stuff, you expect that pin to be at 5 volts or whatever, whatever your transmitter's running at. So if it's hooked right to a NiCad, it might be like 4.8 volts to, somewhere they say 4.8 volts to 6 volts is what RC servos want to see. And, it's not good to just arbitrarily start raising voltages higher than that. And I think we look at that board that Bob, he had it's a saber tooth board, and here, let's just pull up a random one here on YouTube. Saber tooth, it was like a 2x12 maybe. We'll see if that comes up. And it was actually called 2x12 RC. So it's this one right here. And that had me baffled too, because some places you look, the board looks like this with the big heat sinks on it. And then other places look, it has no heat sinks. And this one on the bottom here, which, boy, it would have been easier to pull up a still picture, I guess. Let's see, how can I do that? Anyway, if you look at that, you see it's got on the right here, it's got the 2 RC cables soldered into the board. And then this one up here does not have, it's got a 4-pin connector. I thought, well, how does that work? And if you look at the board, you look at close up, it's got patterns for the RC holes, and that's got patterns for a 4-pin connector. And it turns out that this board will run like 3 different modes of stuff. If you buy the one with the RC connectors, they expect you to just plug that in to, say, an RC receiver, and everybody's happy. And as long as you're putting 5 volts from the RC receiver into that, there's another issue that comes up on that. This particular board says it has the BEC, that's battery eliminator circuit, which means you can make the board put out 5 volts on these 2 cables. So if you're plugging it into an RC receiver, you can actually power the receiver from that. But now if you're running it from, say, a computer that's already got power, or a radio control receiver that's already got power, you don't want two different things trying to drive against each other. So in that case, probably just leave the pin out. So just hook up 2 pins, hook up the ground pin and the signal pin, if there's any doubt about what's going on. And then on the motor driver board itself, put a known valid 5 volts into that, and then you'll be much better off. I think much happier in the long run. So that's just something else that popped up when I was trying to dig through all this stuff and figure out how any of this stuff works. I kept running into funny little things like that. And the story was, Bob had one of these 2-channel boards, like this bottom one with the cables on it, and he had a hook plugged into his Vex controller, which is still a total mystery to me. And he ran it for a while, and one of the channels quit. And then later on, he took it out of the box, and he made a movie in his new house of the thing on the floor, and says, well, my one channel doesn't work. So one of the wheels wasn't turned, the other one was. So it was driving around in circles. And later he was telling us, oh, they both quit at the same time. But no, we've got video evidence that it was running. So one of his channels lasted longer than the other one. And it may be that he had too high a voltage coming out. It's still a mystery what actually caused that. So like I said, no sense watching this page anymore. Let's see, stop sharing. So that's kind of what I did this week. I was just digging through various web pages, both on YouTube and just simply looking out through links. And Bob posted a whole bunch of links. I was pulling those up and looking at them. That's where I noticed the difference between those 2 boards, because you can get the one board that's pre-wired with the RC connectors, and then one just has a 4-pin connector on. And I was also noticed some of the links. One of you pull up, it says it's like a 2x12 saber tooth quick start guide or something. And that one is only talking about the RC inputs. And then somewhere else you pull up a link that says, here's the manual for that board. And that's where they're talking about the multiple input modes, and it's got the 4-pin connector, and it has more information. So it's also confusing when they post this stuff, and it looks like two totally separate boards, and they're not. They're really all the same board. So I was, trying to pull up information on all that stuff and figure out, what might be wrong and what he could have done wrong. Another thing to keep in mind on any of these boards, do I have a handy board here? Let me just grab this. This happens to be an Arduino, but it'll work. So now if you've got a board like this, you're going to put it on your vehicle or something. Keep in mind there's bare pins on the back, so don't bolt it down to metal. Don't bolt it, bolt it to plastic or bolt it to wood or something like that, or put standoff so it's actually standing off the board. Because if you start shorting out stuff on the back of any board, you run the risk of blowing everything out. So that's just another thing to keep in mind, that as you play with it, that's something to no matter what it is, whether it's a power driver or a microcontroller board or power supply, whatever it is, make sure it's not going to short out on something. And a note on that, the last meeting, Al was showing us a picture of his board that he's making for his lawn tractor right now. And this is the first time I saw that he's got a battery charger connected to two big bolts sticking out of his board. My first thought was, one of those is going to fall off and drag across his electronics. It's going to blow out his entire electronics board. So you might want to think a little harder about that. Up to that point, I saw he had these two big bolts sticking out of his board. One had red tape on and one didn't. I kept thinking, what is that for his battery? And then when he showed this last one, he had showed a picture of the board from the side. He's got these two, battery clips clipped onto the thing. And that's what he's doing. That's to charge his battery. But that's another case where eventually one of those clips is going to fall off and it's going to drag right across all of his expensive electronics and probably take the whole thing out. So you might want to think about that a little bit harder. Maybe either put real connectors on there or figure out some way to support those so they can't fall off. But anyway, that's just something else that popped up when I was watching these videos and happened to see what's going on. And talking about shorting things out, I get so annoyed to watch people's YouTube videos. They get crap piled all over the table and they hook this stuff together and the boards are laying on other boards and they twist their wires together and they don't put tape or anything on them. And I'm thinking, why does any of this stuff work? They have no regard for the basic electronics. So that's just another rant that I go into when I watch this stuff occasionally. So let's see. Anyway, on mine.
At work, we used to call those a safety moment. So you're just trying to keep us safe. And for the record, I have 3D printed caps for those for those charging ports.
Well, for the record, if you go back and watch last week's video, you can see you had everything running with those things clipped on there. So.
Well, yeah, I mean, I gotta take some risk somewhere.
Yeah. And you don't think about it until one of them falls off and the whole board goes bang. And
Yeah.
Damn, I shouldn't have done that. So
anyway,
right. That's just more stuff to think about.
And I think you were going to talk about oscilloscopes. You started talking and then we didn't have recording turned on.
Well, let me point out, since I was trying to figure out that 5-volt thing on the board and does the board work? So I just put the whole thing together. I basically just have a big, it's probably isn't the right thing to do, but so anyway, right now I just have a big lead acid battery. Come on, focus. And there's a big motor that's off like an electric scooter or something. So it's probably like a 12-amp motor or something. And they're just hooked up to that, one of those little boards like that. As I was saying last week, I just took the heat sink off my board because I don't want it shorting out the pins on the back. So I took it off and I haven't bothered to check. I could run it and check to see if I doubt if they're even getting warm since the motor's not loaded at all. But if I load it down, then they might warm up. I've got a thermal camera somewhere. I can look at them and see if they're getting hot, and maybe they'll tell me what the temperature is. But so I just simply have that board wired to an Arduino Nano and grab somebody's random code. And basically, I just have it set up right now where it says set the forward PWM to this level and delay for 1 second. And then say set the PWM to 0 and delay 1 second, and then set the reverse one, and it just keeps going back and forth. And I don't know if this would even. Of course, I didn't put any tape on my motor, so you can't see it turning. But and the question was, can you hear it? Maybe if I get my microphone close like this, you can hear it. Anyway, just spinning the motor back and forth, and it proved that it did work. I know, so I grab it, it's got a nice constant torque on it. See if I try to hold, it's got rubber hose on it. If I try to hold it, it doesn't slow down much. So it's everything's doing what it's supposed to. And the chips right now, they don't seem to be any heat at all on those. So that's a good sign. So anyway, I just setting that up to see, can I make it run? And then I was trying to measure that 5-volt thing. And that's what I did on that. And more things as I dug through all the stuff, I run into the fact that, all these different methods, you got pros and cons to no matter what you're doing. And for instance, if you wanted to take this Arduino and measure an incoming RC pulse. So if we try to duplicate what Bob had, he had that saber-tooth board that would directly take an RC pulse coming in and then drive his motors directly. So on this one, if I just add a input connector on this Arduino and connect it to an RC signal, and I've got those again, I like to hold these up every time, but I've got one of those servo testers. It's just something you buy on I think it's just a servo test. That what it says? Server test. Anyway, you can buy on these on Amazon for like $3 to $5, depending how many you buy at a time. And it's just got a knob on. As you turn the knob, it just generates an RC pulse out your cable here. And if you're plugging it directly into, say, one of the giant RC servos, they've got that battery eliminator circuit, which means their connector is putting out 5 volts. So it powers this board from the RC servo. Now, if you got a regular RC servo, what you have to do, you have to go down this end and put your 5 volts and ground in here, or whatever you want to run your servo on. You put that in here and then plug your RC servo in here. So the little servos, that's how you run those. You have to switch your power back and forth. But it's also good that's how you keep track of all your different powers, so that, you need to look at all these things to decide how you want to hook all that stuff up. So if I take this and plug this into my board here, then there's a couple of ways that I saw people were measuring RC pulses. One, you can use something called a pulse in command, and that's just a standard Arduino function. You say pulse in on pin 3 and maybe something else. And what it does, it starts watching that pin, and it waits for the pin to go high, then it measures the pulse width, and when the pin drops, it takes however long that was and returns that. That's a return value. It says, here's how many microseconds long that pulse was. But so the pro is it's there, you hook it up and it just does that. The con is, as soon as you call that function, your processor is completely locked up. It's a blocking function. So when you call it, it sits there and waits to see a low pulse, and then when it sees a low pulse, then it measures the high pulse, and that entire time your processor's locked up. So depending on what you're doing, you could write some code that would waste 90% of your time sitting there just waiting for pulses to happen. And then I looked at some other people's code, and they were using interrupts to do it. So you just tie that incoming RC pulse to an interrupt pin, and then you say attach the interrupt, and the interrupt code simply says, oh, I got an interrupt. Is the pin currently high? If it is, then I want to save the current microsecond timer, micros. So you say start equals micros and you return. And then the next time you get an interrupt, it says, is the pin high? No, it's not, which means it just dropped. So then the second part says, okay, subtract subtract micros from start, or the other way, whichever way you go. And that will tell you the duration that happened. And they just load that into a variable called PWM, and it's done. And at that point, you're using almost none of your processor power to do that. So you're not tying everything up. And it looks like once you start that, just anytime you want, you just go out and read, say, what's that variable I called PWM? You just read it up and that'll tell you the last time that it happened to measure a pulse, which might not be the one you wanted. If the RC pulse went away for some reason, it might be an old value, but in general, that's just another way around that. So the two different techniques, the pros and cons are, the one, it's just a command, it's ready to go, and it returns a value to. The con of that method is it's wasting all of your processor time. And then I noticed, so there's one with the interrupts, it takes a few more lines of code and you have to think about it a while. But once you load that up and start it, it's not wasting all your processor time, and it's just automatically updating these values in the background as the incoming RC stuff is changing. It just keeps updating the values. So that if I would just spend a little more time, I could have got that done. Right now, I just have to hook up the 3 wires from that RC tester to my board here and just hook up the one signal pin, and then either do a pulse in. In fact, I could do it both ways. Say, here's the way it works: a pulse in, and show you the values. And if I get my oscilloscope out, I could probably figure out a way to show, see, it's wasting all of this time here. And you can do that by with an oscilloscope, taking an extra IO pin on your board here. And when you say, I'm going to call the pulse in command, set that pin high. And then when it returns from the pulse in, set the pin low. Watch on the oscilloscope, it'll have a pulse like this saying, here's what started, here's what ended. And just keep in mind in the middle, you can't do anything else because it's got the processor tied up. And that's a handy thing where we're talking about oscilloscopes. That's something you can do with it. You can actually measure things like that. Or you could in your code before you call the pulse in, say save out my millisecond timer or my microsecond timer and save that as my start number. And when the thing returns to you, take that number, subtract the two, and that'll tell you how many microseconds or how many milliseconds, which is wasted time while you're waiting on this thing to come back. And then, so the next thing was, I was saying I couldn't find anything. I ordered like 4 or 5 of these when I first ordered them, and one day I went through and I threw them all in one box to make sure they're all in the same spot. And then when I moved, I have no idea where my boxes are, and this just happened to turn up in a box. I thought, okay, so that's all set. But what I could have done was I could have just taken just a regular potentiometer, hooked it up to something like an Arduino Nano, and then said, read the voltage from a pot, and then in my code, they've got something called a servo library, and one of the functions is generate an RC pulse. And so you feed it the number, and you could get the number off the pot or just type it in from the keyboard, and then it's going to try to generate a pulse that width. And it turns out to say, oh, but if you're running this, you can't use timer 1 because it's basically using the internal timer to I think by doing that, it lets you run. It's not going to tie up all your processor time, but it ends up using fully using timer 1, so you can't use it for anything else. And then the 2 output pins from that, they say something about don't use those, or there's something that's going to conflict or whatever. But anyway, that's a way to do that. But if you go out to this timer 1 function, which we were saying will generate a PWM without it, you could generate a fast PWM, and it generates it in hardware, so it's not wasting any processor time. You can set it to a high frequency, and there was some other advantage to it. But on something like an Arduino Nano, you only have 2 pins that can be defined as hardware output. And it just so happens those 2 pins on that timer is the same thing that if you're trying to read a pot and generate an RC pulse, those directly conflict. So you cannot run those at the same time. So that's a con to both of those. They will interfere. Once somebody starts getting cute, it's going to start interfering with, other cute stuff that people have done, or maybe even conflict with some of the existing Arduino commands. So I had that figured out. I thought I was going to put together a demo and say, here, we'll take a Arduino Nano and put a pot and generate an RC pulse, look at it on the scope and look at all the characteristics, and then explain, you got a full frame time that normally has 8 pulses stacked up. But by the time you get down to a single channel, there's be just one single pulse coming out in this amount of time for the entire frame. And we could look at all that stuff on a scope and see what all that's doing. And then I can either run that or use this to get my RC pulse. So then if we move on the next step, it says take an Arduino or something and measure the incoming RC pulse to tell us how wide the thing is. And at that point, we could scale it to anything we want. And so if we're trying to run, say, a motor driver, the one guy said there's 3 types of way of driving these boards. And I got 2 different boards here that I can do, because I got the one we were just looking at that has a forward PWM and a reverse PWM. And then I got one of those Cytron boards. I got a couple of the Cytron boards, and they want a PWM and a direction bit coming into it. And that's just, just changing a few lines of code to drive one of the others of those. So theoretically, I should be able to say, take one Arduino, feed it an RC pulse, and then have it directly drive the pins to run a motor on my table here. And that should do the job. And when I start talking about that, I'll go into a lot more things, because I was pointing out that the pulse in wastes all your time. And then if you're trying to read more than one channel, if you call it again immediately, it's probably not going to catch the second channel that should be right there. And it's going to have to loop all the way back around. So now you're going to lose, you got to wait one entire frame time plus whenever you call this thing to start it. So you could end up wasting a lot of time if you really want to. And then finally I realized, well, it doesn't matter, because I kept thinking, how do you get these pulses at the same time? Your joystick on your transmitter sends out these 2 channels of stuff, and they're stacked right together. And, ideally I was thinking, well, you have to read them both at the same time, but I was watching this guy's code and he didn't seem to be doing that. I was looking at his stuff and he says, oh, we'll just call pulse in for channel 1. And whatever number comes back, he'd scale it and send that to his motor. And then he'd go out and he'd just call it for the second channel. I realized you don't have to read them at the same time because this stuff's coming out 50 or 60 times a second, the essentially identical data. So you can just grab it at any time with a pulse in, it'll lock on when it finds that pulse, return the value to you. And then when it comes back, when you're all done your processing, just call it for the second channel. And it doesn't have to be synchronized. It'll just simply sit there and wait for it to come through. And you might waste up to say 1 frame time, which is like 16 to 20 milliseconds or something. And so I finally decided that's why you can get away with that. And that apparently would work. So that's something else. I could explain that and we could show it, watch it on scope and see all that happening. Or what was the other thing? So that's one where you could also use the interrupts to measure the incoming pulses, and we can watch that. You can watch that on scope and watch all this stuff happening. So it just seems like, if I just sit down and do this and then figure out how to get my scope traces up on the screen. Whether I say last week I could point a camera at the screen of my oscilloscope, or it's got some kind of a USB cable you hook up, and somehow it reads the data in, and I have to go back and play with that, see if I can get that to run again. And that might just it gives me like a little black and white display, I think, of whatever was on the screen will show up in a window on the screen. So that might work too. And another thing, I would say Terry has that cute little logic analyzer. It's just a little bit bigger than one of these, but it's got like 8 wires coming in here. You hook up to your thing, and USB coming out this side, and you can watch up to 8 channels at the same time. And it has like a 1 megabyte buffer or something. So, and that's real handy. You can make that do all kinds of wonderful stuff too. So if you need to just look at, say, timing and pulses, that will work great. But if you need to see voltages, then you have to have like an oscilloscope. And while I was in the shower this morning, I'm thinking, if you're searching, you might want to look to see, because you could take like an ARM processor, a modern ARM processor that runs really fast. They're 32 bits. They've got probably a 12-bit A to D. They probably even have a DMA hooked to them. You can probably just make an oscilloscope out of any random processor board you got laying around. You might have to look to find the fancier ones to get make sure they're going to be fast enough and have enough RAM to hold it. But you just write up a loop that says, when I start this thing, I want you to grab samples until the RAM's full and then stop. And then at that point, then you can go out and look at the RAM and do anything you want with it. It's got all the values in there. So if you happen to be running, if you're running this through Linux, you could pull a Python and use those cute graphing programs that Al's always using. I can't think of what those are called, but they're like PyPlot or something. Anyway, you can make really fancy looking oscilloscope screens with that. So you have to go through and say, would it be fast enough to, would the A to D and an AVR or an ARM processor be fast enough to be usable to make an oscilloscope? And then you'd have to, figure out input scaling, because of course an A to D wants on an ARM processor go on 0 to 3.3 volts. So you have to figure some front end circuitry that will take your arbitrary voltage that you want to measure and like scale that, use attenuators or amplifiers or something to get it within the range that you want. So it's a matter, if you want to learn how the stuff works, that'd be real cute to go through and do that. Actually build, just take a cheap little microcontroller board and put code in it, and then have it dump out the values to your laptop and then put it up on a fancy screen there. So that's something you can look at. And that's why I was thinking, if you go search on the internet or search on YouTube, I'm sure there's lots of people doing that, and they can tell you the pros and cons of that. And when I say, is it fast enough? I can't quote these things to you right offhand. How fast of a scope do you need? And I don't know. So that's another issue. Because when we get to my oscilloscope, which I'm going to talk about in a short bit here, the specs are it's dual channel. It's a 100 megahertz oscilloscope, and it's a 1 gigasample per second A to D. And the 100 megahertz, that defines the analog section up front. So from the point where I got a scope probe hooked to something, all the amplifiers and everything in between are good up to 100 megahertz. And so you're putting sine waves in or square waves in up to 100 megahertz, it passes that signal through. And then the A to D sample at one gigasample per second. That's pretty darn fast. Your little microcontroller board's not going to do that. But I I'm guessing with the A to D in those and the DMA, you can probably, get it to sample at a, easily get it, probably even without the DMA, you can probably get it to run at 100, 100,000 samples per second. And then maybe with that and the, put the A to D in whatever mode it runs as fast as it can and get the DMA, you can probably get, they might even let you run 2 to 5 megahertz sample rate. But you'd have to look into the stuff to see if that stuff worked. So yeah, that's some of the things that came up. And while I was taking a shower this morning, I was thinking about oscilloscopes, because just an hour before, Bob had said, "Hey, what about these oscilloscopes?" And he pulled up a page. Let's see, how can I find that? If I go back to here and go to here, and okay, I'll just leave it on that screen right there. So if I say, so I'm not screen sharing, right?
Not yet.
So the problem is, the problem everybody runs into. So you just start screen sharing, oh damn it, your Zoom screen goes away. Let me try this again. Open that up, and then go into Zoom here and say share screen, and I want this screen. So this is a screen that Bob popped up and says, "Hey, well, would you suppose any of these would work for a hobbyist?" And if you go look at these, they're the cute little things. It's a little box. Some of them are almost like a pocket size oscilloscope. And let me get this out of the way. And let's see, can I zoom in on this? Let's try Control Plus. No, that doesn't work. So anyway, here's the whole kit. Let's just grab a random one here. And it says check price on Amazon. So let's just take it to an Amazon page. That stuff's small enough I can't even read it. We'll see what this does. So there's a whole bunch of these out there that you can buy, and this says runs at 500 megasamples per second. And that's half the speed of what mine runs at, and in a little cute little pocket device. It does say it's currently unavailable, so we have no idea what the price would be. But it says it says 100 megahertz bandwidth and 500 megasample per second. So that's half the sampling rate of mine. But I was just amazed when it said my oscilloscope would sample at one gig a sample per second. That's crazy. And what was their thing? Scopes. So I'm guessing this is a single channel scope, and I would find it. I always find it very handy to have at least 2 channels. So because we were talking earlier about how do you, why would you want to trigger input? And I said, well, if you had to, say you've got this, in this case, you've got a kind of a sine wavy looking thing here. If you had a trigger channel coming in, you could say, well, I want it to trigger at a certain time. And I can't, well, if you look at the little screen here, say right there, here's the peak on that thing. By changing the trigger looking at a different waveform coming in, you can move the trigger around on that, and this thing would slide back and forth as you change that trigger. But that would be a real pain. You have to, my opinion is, you have to know enough about electronics to know why that should happen in the first place. So to me, if you have two traces on your oscilloscope, so you can watch 2 independent waveforms, you can watch them both in real time and see how they relate to each other. So one of my thoughts is I would probably try to hold out for a 2-channel scope. But if this was $50, I would say go for it. But since they're not going to tell us the price, we don't know. So let's come back here and say, grab another one. And this one is also currently unavailable. I assume this one will be too. Boy, here's one for $35. And they're not bragging about the so first of all, it looks like it's a single channel scope, but they're not bragging about the bandwidth or the sample rate, so I'm guessing it's not real fast. This is probably one where they've just put an ARM processor inside the box and are sampling for that. But you have to read through all the stuff to see what they're saying. But right there, for $35, that would, if you just need to say, is my oscillator running? You want to stick it on there and look at it, or I want to look at pulses. I'm going to generate pulses with my microcontroller. This may be, compared to not being able to look at it all, that would be phenomenal. So for $34. Oh, the regular price is $35.99. I don't know why it's cheaper, but anyway, that's not that much money, and that can be very valuable if you don't, because you can look at square wave stuff. If you have a logic analyzer, you can look at square wave stuff, or looking at your Arduino IDE where it's, you say print out numbers, then pull up the, what do they call it? They have one that's called, it just plots out the numbers on the screen, or you go to the other one that's called, analog. I can't think of what they call it, but there's another one that will actually plot those values out. So, technically, if you're going to use your Arduino to read either digital pins or analog pins, you could, just dump it out on your Arduino IDE and see actual waveforms. So that's something else to just in playing around, you might want to go down that path. And let's see, here's a picture of what's inside of it. I say, there we go. So it's got a little board there. It's got a big board with a display and some buttons. So I'm guessing there's not a lot of parts in this thing. So this might just be like, say, an ARM processor. Like I was saying before, you just have to scale the input and read it and then dump it out. So, and this was nice. It's got a built-in display. I was saying before, you could build an ARM-based front end and send it to your laptop. So basically, what you do is you want to set it up where you configure the thing ahead of time. So I want you to say this number of bytes. I want you to clock the A to D at this rate, and then basically just say go, and then have whatever it takes, to have the A to D loop through and fill up your buffer. And when it's done, then it says, okay, I'm done. And then you can send the buffer out, either display it directly or send it to, say, a laptop, like I was saying before. And it's, this has some pretty simple things here. So connectors for, that's a power connector and a power switch. And then it's got one BNC connector. Another thing I thought of, again, I think while I was in the shower, you can buy these that have like an oscilloscope probe soldered directly into the thing. So you don't have this connector. But it turns out oscilloscope probes either step on them or break them, or they're just cheap when you get them. And if you destroy the probe and you have to replace one and you don't have a connector on it, well, now you have to tear the whole thing apart, unsolder what's there, get another one. You might have to cut the wires off and solder it back in. That's going to be a real mess. But if you get a one like this that has a connector, you can just take anybody's scope probe off the shelf. Because scope probe are kind of magic. You don't want to just use a piece of wire. You have to get a real probe. But with a BNC connector, you just unplug the bad one, plug the new one in, or you can buy ×1 or ×10 probes. There are various things you can do to swap those out too. And then the coupling switch AC DC, that's something that if people want to get into scopes, we could analyze all that, or look on YouTube. They'll explain why you have all these things, and just find somebody that's telling you how do you use an oscilloscope and have them explain all this stuff. So anyway, for $35, you can get a single channel one, which is going to be, that's light years beyond not having anything, just sitting there looking at it. He said they're looking stupid. Well, it's good to know something here. But this one, you'd have to dig through the brag sheet here and see what they're saying for sample rate. It says there's 500 microseconds. I assume it's 500 microseconds per division. And I can't tell you right offhand what any of that is. That converts. Oh, right there. This one actually is telling you frequency, and the cycle is probably. That's probably just the inverse. That's probably the time. That's the inverse of the frequency, probably. But see, they're reading something that's at 1 kHz. So you got to ask yourself, if I need to measure 10 megahertz, is this going to do it? And my guess is this particular one probably won't do that. But you'd have to read through all the their definitions they're giving you here to see, because you could get, say, the old Arduinos probably to sample something 1 kHz. So let's go back and just look at a couple other here for the heck of it. So we looked at these three. This one looks like it's kit, and this one's also currently unavailable, but this is a kit. I think you get I feel they've got a couple of the harder to solder parts already soldered on, and then a bunch of parts to put together. And it's got this one does not have an oscilloscope probe. It's just got a BNC connector and then 2 alligator clips on it. And so some of the magic you get with a scope probe is not there. So again, and this down here is probably it's this show you when you're all done, it looks like that. So it'd be interesting to know what the price of this is. And if you look at the numbers over here, it says it's 1 megasample per second, which is quite a bit short of 500 megasamples per second. And they don't mention any bandwidth here. So you don't know how good the analog section is. Let's see, if we look at this, they were saying
So I looked on Amazon and yours says 100 megahertz.
yes. And typically ones like
that
that,
like
you
1,000 times faster than this?
well, this one so far I haven't seen a bandwidth, which is the 100 megahertz. This
Oh,
is this 1 mega sample per second. Mine is a giga sample per second. So that's what, 1,000,000 times faster, the sample
got
rate.
it.
So and those two things interact. You got to have the analog part to allow the signals that you're looking for, and then you have to be able to sample it fast enough to get a reasonable outcome from that. So I was saying, I was looking at those before. Well, here's this. That's not one I have is a 7102. Oh, this is a Siglent. That's here. Let's see. Here, we had one more to look at here, just because. So far, we only have a price on one, and this one they're not going to do a price either. This is the same kind of thing. It's apparently you get these pieces and you bolt it together yourself, and it's got the same kind of thing with just 2 clip leads on it. And I can't tell you why a scope probe is better, but they just are. And so it's just somebody else's kit, and so it'd be interesting to know what these are. But again, this looks like a single channel, and it source. Oh, this isn't even open source. And I don't see anything about sample rate or bandwidth here. So maybe if you dig through here, it's going to tell you like voltage ranges, and so those just down here, they might tell us something. They're basically just telling us the size and the shape and how the display works. There we go. Here's some stuff. Analog bandwidth, 200 kHz. So 200 kHz is pretty slow. And that's, again, evidenced by the fact they don't have a real scope probe. They just got a clip lead on it. So that's, if you're trying to look at an analog, say a sine wave, they're saying you can look at a 200 kHz sine wave and it should still be an accurate signal coming through. And then going above that, because what did I say? Mine was 100 megahertz. So 100 megahertz is what, 5 times, was that 50 times faster on the analog section? And then as it gets samples per second, and these ones that are slow sample per second is probably they just put an ARM chip in it and just run at whatever speed the chip will run at. And maybe it says it there. It's not popping right out at me. So, and if you go look for it, there's other people building these things that, again, if you got time and you just want to see how this stuff works, and what's this one? Detailed assembly manual. So I assume it's the manual for the one we're looking at right now. So let's go back to on Amazon. Where did I find? Right here. And the Rigels are basically equivalent to what I've got, but they got the smaller screen on. And then the Siglent here it's got the larger screen. And I see mine isn't listed at all here. So if I say 01 oscilloscope, I don't know if I should spell oscilloscope, but we'll see what comes up. And they got some pocket ones here. So here's one for $185. This one probably is 2-channel because they get 2 scope probes with it. So this is like a miniature version of what I have. And here's another one. It's a miniature version for $300. But I think I saw you could get one like I have, a trimmed down version of what I have for like 300. So see like this one. Here's one. You'd have to read all these, but it says 200 megahertz bandwidth. So that's better than mine. 2+1 channels. So that means it's got the two input channels and a trigger input is what 2+1 means. I took me a while to figure that out, but 2+1 channel, three in one functions, 25 megahertz waveform generator. So this actually generates something out too if you want it to. So again, if you just dig through those, here's one like a bench top about the size and shape I have. It's like twice the bandwidth. I don't tell me sample rate here. It's $100 cheaper than the one that I had. And here's and you know, probably even people like Fluke and those the people that have meters and stuff, that I think they make little pocket oscilloscopes. So again, it's just a matter of finding. And here's a just a box you lay on the desk. You hook your thing up and then you hook it up probably to USB, and it's $120. So you have to look at the specs and say, you know, is that good enough for what I want? And if you don't need to have all the knobs and buttons and the LCD display right in front of you, that might be another way to do it. So especially if you're trying to do it, say, automated test equipment, you might want to get something like that. So just in general, digging through here, this one looks a lot like mine. This might even be, you might even get one that's got, like, say, two analog channels, and maybe this says right here, it says it's 4-channel digital sampling oscilloscope, 4-channel digital desktop. So this probably is an actual 4-channel scope. Give me an image here. So probably the 2 bottom channels just don't have anything on right now, so it's just showing as orange and green. But you know, theoretically, it should give you four actual traces at a time. And a 4-channel scope is handy every once in a while. You know, for the same reason why a 2-channel one is better than 1-channel. You got a 2-channel scope. Oh, I just want to see one more thing, and that's where you start doing tricks with the trigger input. You know, I got these waveforms, but you actually want to know what's happening here. So you hook it up to a trigger input. There's a pulse out here, and that way you can slide stuff back in front of the screen and look at it. But again, it's just a lot of, you know, digging. And this one says it's a 60 megahertz bandwidth. So I assume that's 60 megahertz on each of the 4 channels, and it's got 1 gigasample per second. And typically, if you got, say, a single channel scope, that means you can sample it one gigasample per second. If you turn on 2 traces, then it's going to sample half that rate. And in 4 channels, it's probably 1/4 that total rate. But I don't know. I don't know that for a fact. That's, again, you'd have to dig through all these specs and see what's going on. You know, mine came with this CD-ROM here, and that's the one that you load that on your laptop, and then you can plug in the USB cable. Actually, mine's got USB and it's got Ethernet and something else. Oh, it's got a host USB and a device USB. The device USB, you plug in a flash drive, and then you can just hit some button. There's some button on the screen, or you hit that, and it takes it does like a screen capture out to your thumb drive. So that's another way. If you don't need to do it in real time, you can capture those, then put them in your documents, or I could pull it up and say, well, here's it. I can put on my screen right, say, here's an image that I did, you know, at some point. So that's another way to do that. And I was trying to find the one. It's also hard because you look at these and they say, you know, here's one for 429. So that's about, I think, what I paid for mine. And mine was just a 2-channel scope. So, you know, looking at it now, probably, oh, there's mine right here. And it says it's a 7102, and it's $560, which I don't know why it's so damn much, unless this is the battery. Because mine, you can also buy an external battery and plug it in the thing, so you can actually carry it around and use it. And I never bothered to buy that. I just got a power cord on, I run it that way. So there's all these different ones. So my screen, the front of mine looks like, how do I do this? Like this. That's close enough. So that big thing there, that might be a battery. I don't know what that is. It's something that would have to account for an extra, what, $150 over mine. So here they give you multiple probes. There's a USB cable. And on mine, see, it's got these white buttons up here. Those are some kind of function buttons. And one of them you press it and it turns on the cursor, so you can move the cursors back and forth on the screen. You can move those to measure time, or move them up and down to measure voltages. And then around the side here, it's got function buttons along the side, and I think these are more function buttons, where they call it W1 through W5. And I don't remember what so when the thing's running, it puts up, it creates a menu on the screen here. It says, oh, so press number F2 to, say, start the trace or whatever. That's what those are for. And it's kind of a pain. It's got knobs on it, but these are all digital knobs. They're not, I don't think it has any potentiometers on it. So if you want to run say the centering of your trace up and down, I think it's probably one of these, you grab it and turn the knob, and the trace moves up and down on the screen. Or these might also be maybe because you have to have one knob that moves it up and down, and then another one that changes like the input sensitivity. You want to measure 1 volt or 10 volts or 1,000 volts, and you turn the knob to do that. So it's I prefer. I learned on an old oscilloscope that had a CRT and had regular knobs on it. So they're either detented mechanical knobs or potentiometers. And that way I felt that much more intuitive. But the fact that these knobs basically still work the same way. You turn the knob and it might have little detents on it, but it's like a digital knob. So you can go around and around and around if you want. But it's still, just like a pot. You want to turn it up or turn it down, it still works the same way. So it's just a matter of yeah, I'm not sure. I can't say go out and buy this particular scope or some other particular scope. I at this point, it was this rather quick notice on the whole thing. I thought, well, what would I say? I would prefer a dual channel scope, and I want one that's fast enough to, especially a digital one. I want one that's fast enough to be usable, because if it's too slow and you can't see anything, well, it's going to be worthless. Like that one we're looking at, it says they're reading a 1 kHz signal. Well, if that's all the faster it goes, then you can't use it for most of the digital stuff on a microcontroller. You may not see the pulses in the first place. So just more things like that you have to deal with. So I was just simply going through here, and where was that? And this is the scope that I've got right here. And so I don't know why it's at least $100 more than the one I bought. I was thinking over time the price had come down. Maybe this is a one that somebody of their own they're selling. Yeah, you have to dig through and see what it says, but it says on store, so maybe this is a brand new one. But I know, so you go to the store and they don't seem to have a whole lot of stuff listed here, and I didn't quite understand that either. This was like last week. I was digging through here trying to see what they have. So here's a I don't even see the number on it, but it's 2-channel, 100 megahertz, 1 gig of sample per second, 7-inch display. So this basically what I have, but I don't see the part number listed. And they seem to have, maybe look at it this way. It's an SDS 1102. And I don't know what that means, but the fancier ones here, they've got, if you look on the right, you can see on the bottom, they captured that waveform, and then the top is the zoomed in factor. It says you get something like that, saves like 1 million samples or something. And then if you look over here on the right, there's a little slider that goes back and forth, and that tells you where you are in the buffer. So you can you can record a big chunk of stuff and go back and look and say, well, what happened 10 seconds ago or something like that. So they're just more fancy features that they can build. So the more money you spend on it, it's got more of those kind of features. And see on this one, it's got the two channel input. So you hook up two scope probes, and then mine has an extra one that says external trigger in, and this one doesn't have that. So just things like that, you got to look back and forth and say, do they do what you want them to or not? So let me back up again. So there's lots of scopes here, and that's why you should go out and look for other people's opinions and all this stuff, and say, say, oh, well, look for this or look for that, or if it's especially find the ones that say, well, if your scope is too slow and you're trying to look at these waveforms, see, you'll notice here you can't see them, and that's why I was saying go out to like EEV Blog. I think that's what the guy's name is. Here, let me just pull it up. Let's go to YouTube. Now that guy's pretty entertaining, if nothing else. So we'll go see here and we say, come on. You need to get some big nitrogen cooled computers so they're faster. EEV Blog. Let's see what that does. At EEV Blog. And he's got all kinds of stuff here he does. And I can play a short section here so you can hear it, because he's Australian, and he's pretty funny to listen to. But he's probably got, let's go to his channel. And let's search for
Jones from the EEV Blog, and my secret talent's a bit unusual. Every week I educate and entertain nerds like me.
So I don't know if you heard that, but that's what he sounds like. So you can say search. Is that search? Oh, there it is. Oscilloscope. So yeah, introduction to the oscilloscope, how to not blow up your oscilloscope. That's probably a good one to read. I had a guy who tried to blow up an oscilloscope in front of me one day. I said, "Don't do that." He wanted to proceed on. So here's oscilloscope tutorials. So he's got lots of good stuff here. So let me just back up and say,
Just so you know, I'm not being rude, but I'm going to have to scoot soon.
okay. Do you have anything you want to interject instead of me babbling here?
No, I'm good.
Okay.
I'm good.
Okay, let me here's my chat. And I'll put that there and say, oh, that's going to bring up the whole thing. So anyway, that if you click on that, that'll bring up his channel and show you all the this oscilloscope I just looking at stuff I was looking at here. So there's him, and then there's the guy with the Swiss accent. Anybody remember how to get to his page? I'm totally drawing a blank on what his stuff's called, or I just know he always starts, oh, I'm the guy with the Swiss accent. And so anyway, he's probably got stuff on oscilloscopes and tutorials and stuff. So maybe just go here and say oscilloscope tutorial. Oscilloscope. Real. Oh, here's what it says. Avoid doing this because he's got his oscilloscope's on fire. That's probably part of the thing. Is this, here's how to not blow it up. So yeah, there's tons more stuff there. So let's just say that as a link just for the heck of it. And then you can probably find ones where people are building their own, building oscilloscopes and telling you how the pieces work, and that stuff's kind of good to know, but it may not be what people are looking for right now. So back to the original question is, what about these? Will they work for hobby stuff? Well, that one was $34 and may not be fast enough to, to say, look at microcontroller pulses or whatever. But if nothing else, there's times when you really need to have an oscilloscope. Like say, if you're looking at, say, on Bob's Vex controller, it says that the motor control port, and if you look at the voltage coming out of the pin, that'll show you the voltage, and if it's not a constant DC, it would show you that too. So it might be handy to have that. But again, I think you need to go out and look at to just see what everybody else is talking about. Look at the tutorials, and there's going to be lots of people say, "Oh, here maybe oscilloscope selection." Maybe search for that and see what it says. Here's guys saying how to use it, and in showing you how to use it, they're going to say, "Well, it's going to work, for different frequencies." Yeah, are we going to be able to see that frequency because of the scan rate and all that stuff? So anyway, I say I can't just off the top of my head tell you what you need to get or what's a good brand, or I just know I've got one that works. And I've been fairly happy with it. And every once in a while, boy, I wish I had a 4-channel scope. So you have to look at if you get that far, you have to say, well, here's the price of the 2-channel one. And for this much more, I get a 4-channel. Is it worth paying the money on that? So, and maybe it is. I just haven't looked in a long time. So here we're back to how to not blow up your oscilloscope. Because you have to remember that the ground pin on your oscilloscope lead is usually tied to the ground pin on your power cord, which if you start poking that around, hook it up inside of a box that doesn't have isolated power, it's going to go bang. And it's going to blow the lead right off your oscilloscope and maybe take out half your oscilloscope. So that's the things you want to know when he says not how to not blow it out. So you want to look into this stuff. Here's one's called What is an Oscilloscope? So anyway, that's my recommendation. Just search YouTube, just go to regular, like a Google search, and say oscilloscope basics, how to choose an oscilloscope. And I'm sure there's gonna be tons of stuff out there to tell you what you need to know. And I'm sure right offhand, you probably don't know what you want to do with it, but that's part of the thing. There's things every once in a while you need to be able to see that stuff. You think, well, gee, if I had an oscilloscope, I could look at that. So that's probably where the main part of that comes from. I've had this oscilloscope for like 4 or 5 years, and I've used it about 6 times that amount of time. But when I need it, it's real darn handy to have that. And the fact that the modern digital ones will actually, you can save the waveform. So you hook it all up and say go, and when a condition happens, bam, it saves the whole thing. And the one with the big buffers, I can back up, 10 minutes and say, what was that wire doing back there? When the whole thing, when my processor reset. So you could be watching your power line and then have somebody detect the power reset. And then when it stops, you can go back and look and see, did I get a power glitch or did something else happen? So without just rambling, I guess that's about all I had to say on that. Is do you have things you want to talk about this week?
Not me.
Okay, well, let's see, I talked about motor stuff, talked about oscilloscope, and I'll try, but if I again get back to the thing, I keep saying I'm going to put together some demos. If I do that, I throw my oscilloscope into it, then we can that'll give us more to compare all this stuff together and decide, do we need a scope or not need a scope? So so maybe next week we'll have a little more to just to add to the all the stuff we're talking about.
Yeah. Questions for me would be pulse width modulation versus RC modulation.
As far as oscilloscopes, or for just in general, you're talking about?
Just in general, how the signals compare. I've been reading online, and I need to look more at that duty cycle, especially where you can't go over 98%.
And that's based on the driver board itself, the way they're driving the MOSFETs, because in order to drive, you can put in all the same kind of MOSFETs. You can put all in-channel MOSFETs, but the top MOSFET, you have to drive the gate at a higher voltage than what your incoming power is. So they've got a cute circuit on there called a charge pump. So as you're switching the MOSFET on and off, you got like a diode and a capacitor. What it does, it takes your supply voltage and puts it on that capacitor. And then so here's your gate voltage here. And so as it's running, you have to be like 10 volts higher than the incoming power. So you have to create that with some kind of external circuit. So they're using that to do it. So as the thing switches on and off, every time it comes down like this, it then charges that capacitor. So this comes on like this. Now your gate comes up here, but your power supply is actually like 10 volts above that. And that's what they're trying to, and the problem is if you stop switching, what happens is that well, it's not only backwards, left or right, backwards, up and down or something. Anyway, so you got this, say you're running on 12 volts. So the bottom MOSFET, you can switch it with 12 volts. At the top ones, you have to get higher voltage. So you got this higher voltage up here. It might be running, say, 20 volts. And as long as you keep switching the thing on and off, it keeps that charged up. But if you stop switching, then that capacitor starts discharging. And when it gets down to the point where it has no ability to turn those MOSFETs on anymore, you go through the linear region, you might just smoke them and blow them off the board. So they're saying, as long as you keep this moving all the time, even if it's a very narrow pulse, that will keep the capacitors charged up and everybody be happy. I think that's what they're talking about. So it's the way they built the driver board, and on their particular driver, you must do that. So that's why they specified that, and I think that's why that's what can cause the problems on that.
Okay, thanks.
As far as the difference between PWM and RC pulses, well, it turns out that PWM is just a generic word. That means pulse width modulation, and you can have 0 to 100% pulse width modulation. That like Vex is calling PWM. You can have an RC one where you've got a pulse. You got a pulse that repeats. Here, I get some extra stuff in the way. Then you got this pulse that varies from 1 to 2 milliseconds wide. And by changing the width of it, that's considered pulse width modulation, because you can controlling the width of it. But this resides inside. You got a frame this big, and you got this little pulse out here that's doing this. That's the difference between those two. So if you're trying to drive a motor, you want to be able to go from 0% all the way up to 100% on the pulse width. And the wider that pulse is, the faster your motor turns. That's what the difference is. And you keep in mind, they're generically using the term PWM because they think it means something specific, and it doesn't. So that's what adds a lot of the confusion on a lot of the stuff in robotics and computers and just life in general, where people will use a term and two people don't think it means the same thing. So that just makes it more complicated.
So in theory, an PWM going into an RC motor driver, it shouldn't destroy the motor driver per se. There's something else going on that would wreck it.
Well, it's very possible that when you plugged that directly into your VEX box that was supplying your motor driver that wants 5 volts, you're supplying it with 8 to 9 volts. It is possible that blew out something on your board. But no, if you, it's in fact, if you go watch YouTube videos, they'll say, "Oh, here we'll take this and we'll directly drive. We'll take the RC pulse out of here, which is just a little short 1 to 2 millisecond pulse every like 60 times a second." And they show it, the diagram on their thumbnail. They say, "Oh, here, run this without an Arduino." So they'll show something like this connected to, just a driver board. So like one of these, they say, "Oh, you can use these 2 things to make it work." It turns out they're not doing that. If you go look at their video, they're taking this controller box and they hook it up to an old RC servo that they've ripped the motor out of, and they take the 2 motor leads and hook them up on this board. So even though it makes it look like that, in fact, a few times they even take a signal like this and hook right to a board like this. And what you're going to see is the board is always going to run the same direction at what appears to be the same speed, because that 1 to 2 milliseconds is not enough to directly affect the motor speed. So it's not going to destroy it, but it's also not going to give you the speed control that you're looking for. So you have to either put that's something else I was going to mention, because I was digging through this stuff. I forgot about the fact, yes, you can use an RC servo to decode the RC pulses that are coming out of your RC system. And then if it's normally driving a motor directly, with those little motors, but as people point out, you can just unsolder the wires and hook those wires up to one of these power driver boards, and that'll do the same thing too. So these boards, you get these boards for about $10 single quantity. And if you get several of them, you can get them down to like $6 a piece or something. And then if you take an old RC servo or a brand new RC servo and just hook the wires up to here, now for whatever the cost of the servo is, you can probably get those for $2 or $3 a piece if you buy them in quantity. And these boards you get them for, say, for $6 a piece. Now you can basically, it should do the same thing you're doing. But again, don't use that 8 to 9 volt pin coming out of your VEX controller, because that's just not what anybody's expecting. So just simply don't hook that wire up at all. And if you have a driver board that wants a 5 volt input, just find out the valid 5 volt supply somewhere and use that instead. So I'd say don't ever hook anything up to that output pin that's not at 5 volts on your VEX stuff.
Yeah, I haven't done it so far.
Yeah, it could be if you dig through your documentation, they'll say that's what it is. But all those links you're posting, I was digging through, and it looks like, yes, they intend for that to be basically connected right to the battery coming in. And then it goes to what they call an MC29 motor driver module. That's a VEX thing. And it's apparently expecting that direct battery voltage into that. Then you hook a motor up to that. So that they simply decided, well, we're building it ourselves. We can do anything we want. And if people hook up an RC servo to it, that's their problem. We didn't tell them they could do that. So
okay,
it could be your VEX box has connectors, say RC servos, and then you got some say motor driver connectors or whatever they're called. Anyway, and I can't find any information on that stuff.
yeah. Well, I'm going to go through all the links and reread it and try and organize it so I understand it better.
Okay. And all those links that you posted, some of them were forum posts, and I kind of, by piecing enough of that together in your mind, if you know kind of how it's supposed to work and what seems to be the problem, what looks weird right now, you say, oh yeah, somebody just made a comment that, that is 9 volts. And well, okay, well, if it's 9 volts, don't hook it up to something that's 5 volts. That's just common sense there. If you know ahead of time what those things are. It might be good to go around in your VEX box and anything that coming out that should be a power driving pin, measure them all and see if they're 5 volts or 9 volts or something else, just so you know what's on them. And if they're all at 9 volts, don't directly plug anything into those for power, to expect to get something on it, because you have no idea what those are actually doing.
Okay, if on the control pin coming out of the VEX, I think it said it's normal PWM 5 volt logic. So if I just put a cheap VOM on there to measure the voltage, will that meter load it down or give a misreading or?
Well, you probably get a misreading because it's putting out little short pulses and your meter's expecting to see a constant voltage.
Okay,
So this is one case where the oscilloscope would be very handy to have that because
yeah,
it's not, even if you measure the logic signal, just on or off, you don't know if it's a 3.3 volt high or 5 volt high signal
Yeah.
coming out of there. So
okay,
I'll give it a little bit of thought because I did think about that before, that yeah, it's occasionally you want to know what is actually there. So
yeah. Okay. Got a lot to chew on.
and back to what I was saying, you could build an oscilloscope out of any cheap microcontroller board, but technically just to find out something like that, you could probably just say if you use like Arduino type processor, it's got a 5 volt analog input. So that way you can probably, hook that up directly and just say sample at a fast rate. And that's probably gonna tell you enough of the time you can see what the value is. That might tell you which it is. It almost seems like somewhere they should tell you in your whole VEX thing, what those signals are, what the values are. Because
Yeah.
I bought a long time ago, I bought two pair. So I've got a transmitter like you have. I got the little yellow receiver box, which I assume you have, that's plugged into probably your VEX controller. And
Yep.
that one at the time, there was information available online. And it's the receiver's got 3 pins. It's got a ground pin, a power pin, and then the logic signal. And I think it wants ground and 3.3 volts for power. So then the outcoming signal might have been a 3.3 volt logic, or maybe you had to power the box with 5 volts, but I think it's still at a 3.3 volt logic output from it. But that's back when I could, look it up and find out what the 3 pins are, and then find out. I think they actually told me the voltage values, but for whatever reason, I can't find any of that old stuff at all anymore. They just want to point me to the whatever the latest junk is, and that may or may not apply to the old stuff.
Okay.
And depending what you're doing with that VEX controller, I was originally using that VEX receiver, decoding that directly with a radio control or with a microcontroller. So it was giving me 8 channels of numbers coming out of it, and then I just did what I wanted with those. So I don't know how much extra stuff that big VEX box is doing for you, other than it breaks out the channels onto connectors that might burn out your motor drivers. So that,
Maybe I'll pop the lid and take a look.
well, is that any labels on the top or the bottom that tells you exactly what generation it is, or does it have a part number or anything? Something I can type in and search for?
There is a part number on the back, so I'll look at that.
Okay. Because that might be all it takes, is then go search and find out and have it pop that stuff up. So
Yeah. And a long time ago, I found high school kids using that system on a regular basis, including changing the programming and all of that. But I don't want to get into the programming of that thing as much as I want to get back into the Raspberry Pi stuff. And my whole thought was, oh, here's something quick and simple. I'll just throw it together and I can get remote while I'm working on camera stuff. But I say I got to do some more reading.
yep. And maybe by next week I'll have something that says, here, look, this works. It takes an RC pulse and drives motors.
Sure.
So we'll see. We'll see if I get that far. Now there's the issue on that new board you bought, where it's got that 98% PWM limit. That kind of limits you slightly, because then you really do need like a microcontroller in between to say, don't let the pulse get any higher than that. And because the other thing is, when people are taking the RC servos, that would be, I think everybody looked at that one time, and I don't think anybody ever finished it, but just a cheap $3 RC servo, and hook the 2 wires up that and hook it up to this driver board here. It should do the same thing and not have the limitation with the 98% and all that kind of nonsense. So if again, I've got a box that says RC servos, and it's got about 100 servos. I got some continuous rotation, some medium ones, some small ones, some micro ones, some big ones. And of course, I don't know where that box is. It's in one of my storage units somewhere. So if I just happen to run across, because I think I keep seeing just one of the micro servos laying around in one of my boxes. So if I find that, I'll probably just rip that apart. I could try that out and hook it up and you know, say that, yes, these two to work together and look, and they say, yeah, I can run it and just watch this motor run. So,
Okay.
so anyway, so anyway, that's all I got for this week. And if you come up with that part number for your VEX stuff, that'd be handy to know. Maybe even on your transmitter. See if I could find my transmitter and my receiver that would have numbers and something on it. I could look it up, but yeah, those are buried too, so I can't find those. So that'd be handy since your stuff's all out. You know, if anything has part numbers on, write them down. And
Yep, I will.
okay, so I think we're all done.